Hey everyone, it's Mary Jane, and my friends and I are here to introduce you to crystalline solids. But first, let's discuss the safety aspects of this lab.
Hey guys, as in any general chemistry lab, it's important that we wear our lab aprons and our safety goggles. Now, since we'll be dealing with liquid nitrogen in this lab, and it can be very cold, around negative 321 degrees Fahrenheit, it's very important to avoid skin contact with that substance, or your skin will become harder than these lab benches.
Hey guys, it's Yas, and I just wanted to remind you guys that if you put something in liquid nitrogen, make sure to wait until it returns back to room temperature before you touch it.
And I'm sure you don't want anything to happen to those hands of yours, so please use plastic tweezers when handling any rare earth magnets or superconductors, as they may be toxic. Also remember to wash your hands after the lab is complete and inform your TA if any spills or other accidents may occur. In this experiment, we'll investigate the composition and properties of crystalline solids, a very unique class of materials.
Primitive cubic cell and body-centered cubic cells are composed of two different arrangements of square array layers. As you can see, we see the square array layer here, and also in the body-centered cubic cell here.
Let me take this. Now, the primitive cubic cell is formed from the arrangement of a second square array layer directly over the first square array layer. And the packing arrangement that results from this is the repeated order of these two array layers here. Now, the coordination number for this structure is 6. And this coordination number is defined as the number of spheres that are touching a specific sphere of interest. Now, each lattice point or ion within the structure is touching in this structure. Now, using the Pythagorean theorem, e squared plus d equals d squared, will allow you to find the length of this face diagonal using the two edge lengths E that you have in this structure.
And if you'll follow me to the whiteboard now, we'll discuss the characteristics of the body-centered cubic unit cell. BCC unit cubic structure is more efficiently packed than primitive cubic unit structure. The first square array layer is slightly expanded in all directions, and that's represented by the green dots here. The second square array layer is imposed on the first square array layer, but the spheres of the second square array layer nestle in between the spaces of the first square array layer. This is then repeated in the order of an ABA pattern. The spheres of the BCC unit cell touch along the body diagonal. The packing efficiency of a BCC unit cell is 68%, and the coordination number of any singular atom is 8, as can be seen in this diagram, where the central atom directly touches 8 spheres along the corners of the cube.
Now, if you guys follow back over here, I'll be able to explain to you using a structure, the cubic closest pack structure. Now, the cubic closest pack structure results from the closest packing of the array layers here. Now, the second array layer in the structure is formed over the half of the holes that are formed by the first structure, and then the third array layer is then formed by placing that layer on top of the other half of the holes from the first structure. Now, the coordination number for this structure is 12, and the packing order for this is A, B, C. And there is a packing efficiency of 74%.
In the example of sodium chloride, we see that larger ions sit at the lattice points of the unit cell, and the smaller ions sit in the depressions or holes of the unit cell. In close packed array structures, we may have tetrahedral holes or octahedral holes. In square array structures, we may have cubic holes or octahedral holes. In this lab, we will be examining nitinol and a 1,2,3 superconductor. Nitinol has two forms, one austenite, which is body-centered cubic and is more ordered than its counterpart at lower temperatures, martensite, which is more disordered. Austenite occurs at higher temperatures and is therefore more ordered than martensite. We will also be working with the 1,2,3 superconductor and is named 1,2,3 because of the ratio of the atoms of copper, yttrium, and barium. We will place a magnet on top of a superconductor that has been cooled by liquid nitrogen. This will induce a current that will then cause the magnet to repel and levitate.
The memory and acoustic properties of nitinol will then be observed and compared to cubic unit cell models of both martensite and austenite, two forms of nitinol. The austenite form, and this is an austenite rod, will make a characteristic ping sound when it's dropped on a lab bench, and the martensite rod will make a thud sound, a much more muted and less resonant tone.
Remember to have fun, you guys, and chemistry is beautiful.
Beautiful.